Hey guys, what's up? Eddie Aho here with KissAnalog.com, and we have EPC, Efficient Power Conversion Lab. These guys make the GaN FETs. Yeah, these GaN FETs are pretty amazing. You guys have seen them if you've been watching my thermal camera reviews. I've done like 5 of them in a row. I did a series. And we've been looking at this little board here. It's a 16th of a brick. A brick is one of these guys. It's a DC-DC module. They came up with the form factor years ago. People didn't have power supply engineers. They still don't. But they could, it was a mystery. So some of the power supply companies got together and they made these bricks, a form factor that people could just design to. So this is a half brick. Full brick would be twice as long. They all come in about standard height, standard pin layout, inputs and outputs. So that was easy to use, okay? So there's an 1/8 brick that's even smaller than this. And one of the things they would brag about is how many watts per cubic inch, like how many watts we can get out. This half brick right here is a 100-watt module. Now, back in the day, when this came out, that was impressive, okay? And now, this little 16th brick, meaning that you can put 4 of them on this guy. That's how small it is. It's 300 watts. So let's come over. I'm going to take you through some data sheets. I'm going to show you how cool this thing is and how these evaluation boards can really help you test the product. This is 48 volts in, 12 volts out, but you can design it with different voltages if you wanted. But this is a common voltage scheme. So yeah, pretty cool, huh? Now, so it's meant to, these companies, they put together these things so you can evaluate them. You go, wow, I like this. Okay, my design has 8 volts or 20 volts or 24 volts. So I'm going to design, and I want a different board shape, and stuff like that. So anyway, let's just come over. Let's go through some documents. Maybe it's kind of boring stuff. Maybe it's kind of fun stuff. Let me know what you think. But I just want to show you what this is all about, because we've been looking at it with this thermal camera series that I've been doing. I think I did 5 of them. And by the way, you're going to see a flare thermal picture in the documentation for this. It's funny. Companies like this, they'll go off and buy brand names, Fluke meters, flare thermal, cameras, not really knowing the best equipment to buy. And they could save a lot of money by buying better equipment. But yeah, it's just interesting the way things are. So let's jump in this video. All right, guys, so this is the EPC9157 development board. We got 300 watts and a 16th brick. So this big board is just a carrier board, okay? The little board here in the middle, that is this little guy right here. That's the 16th brick. Inductors right here, 4 GaN FETs. Let's take a look at these. Here's some efficiency curve, and look, all the design files. So you can download schematics, get all the design files, and the efficiency is only 90% when you're down here around under 5 amps out. As the current goes up, you get 10 amps, start getting a lot more efficiency. So 10 amps, 12 volts, it's like 120 watts, so around 120 watts. You're starting to get more efficiency. Now the thing is as you put out more power, you dissipate more power within the module, right? But when you're down here, say 5 amps into 12 volts, you're 60 watts. So at 60 watts, you're dissipating a little bit more, but let's say 8% is dissipated in heat. At this point, 8% of 60 watts isn't that much. As you go up and you start putting out more power, you want higher efficiency so you don't dissipate even more power. So now you're up around over 95%. Looks like about 14 amps. Okay. Now, if you're only 36 volts in, you get an extra percentage point of efficiency. Okay, guys, this is the evaluation system for the EPC9157. It's a quick start guide. Look, 18 to 60 volts in, quite a range. 12 volts out, up to 25 amps out, 300 watts, okay? Now, this is for December 2020 and version 1. I think this is the latest one, so they must have done a good job and didn't have to come out with a new version. Now, here's the module, the top board. Now, we're going to take a close look at this. We have 2 inductors on the top side. And look, here's 2 GaN FETs right here, 2 more. And look at the diode next to them. They're the same physical size as the diode, it looks like really close, right? And these little resistors down on the board, they're 0402s, okay? So just give you an idea how small this stuff is. Now, if you imagine this board just being flipped like this end here on the left, see it's got 3 pins, 4 pins to the right. So the input pins are on the left, the 3 pins. If you just flip that over to the right, rotate it over, it lands down here. So now they're on the right side, okay? And the reason I want you to see that is this control chip right here. It is, if you look at the top layer, it's right underneath all these support parts, okay? So all those resistors, capacitors, and everything, they're all crowded together. They're all feeding into the pins of this chip. And it still has a few more on this side. And then we have all our input capacitors in this kind of horseshoe shape. And up on the top, it's kind of a horseshoe shape, right? And then if we look at the bottom one again, the output is all these capacitors. So if we look at the top picture again, there isn't any components really. There's one little one right here, but most of them are on the back side of the board, okay? And I imagine these straps right here. See that? Yep, R004. These are current sense resistors, I'm sure of it. See, look how wide they are. So I'm guessing they're 3-watt resistors. Current sense. So we got 2 outputs parallel together to get that power. So here's the electrical specs. Some more efficiency curves. Oh, here off to the right, we've got the power loss. So remember 5 watts I was saying? So 4 watts is being dissipated on the module. Then it goes up, let's say it doubles to 8 watts. Let's say 48 volts in. About 12 amps, okay? So start off around, say, 2 amps, then maybe 12 amps, it doubles. Then we get another 4 watts dissipated at 20 amps out. So at 25, we're dissipating about 14 watts in that little card. So we're going to need some cooling. And we're going to look at this output voltage ripple. We're going to see if we see something like this. Here's the typical transient response. Okay, V out versus I out. So if the I out is, this is 5 amps per division, guys. So this is stepping, what about, does it tell us? From 50%, 12.5 amps to 25 amps. So from half power to full power. And we're getting these little blips. And the voltage per division is 500 millivolts per division. So this looks like it's dipping about 300 millivolts maybe each, overshoot and undershoots. Okay, so when power's applied and the enable pins applied, this is the ramp up, okay? And this is 10 milliseconds per division. So it looks like about 1 division, maybe a little bit more. So 10, 11, 12 milliseconds rise time. Nice and easy, no overshoot. Okay, here's our load regulation. On the left here, we have voltage up and down here on the graph and current out. So at real light load, just a few amps, it's going to be right at 12. And it looks like at 25 amps, we can drop down to 11.8 3 maybe. So we're going to drop a little bit of voltage. All right, and then here's temperature versus output current. So 25, we're up to 90 C. And that's with 1,700 liters of, what is this, LFM, forced air cooling. Okay, operating conditions, so they tell you about all the ways to, to use this thing. If you want, if you want to have remote on-off, turn it on and off. This resistor appears if you want to trim the voltage. So you might want to trim the voltage because maybe you want the voltage to start off at 12.1 or a little bit higher. So at full load, you don't drop below 12. So you can trim it here. And there is a sense pin. So you can use a sense pin to go, to the other end of your cable so that you can compensate for the cable loss. Okay, mechanical dimensions. 33, look at this, 33 millimeters long, 1.3 inches, and 22.9 millimeters across this way is 0.9 inches. And it looks like from the bottom of the pins to the top of the inductor, we have 9 millimeters or 0.35 inches. And then these standoffs, we're using these pins from the pins of the inductor, I think that is. Oh, from the capacitors. Those are the components on the bottom side of the board to the bottom of the pins is 3.8 millimeters or 0.515 inch. And here's the pin out. Okay, plus VN on off, minus VN, plus V out. You got your sense, trim, power good, and V out negative. Guys, check it out. They're talking about thermal management, and look, they're using the FLIR thermal camera. Now I've done 5 different cameras recently showing this board and how good a resolution those cameras get, and I would say every one of them did better than this camera. So yeah, maybe I'll flash up a picture to compare to this. And Renaissance, they're giving a shout out to them for that chip they're using, the control chip. All right, guys, the star of the show is this GaN FET. Look at this, 3.5 millimeters long, 1.95 millimeters across. And very interesting pad work, right? This is good for 100 volts drain to source voltage. The RDS on is 3.2 milliohms, and it's capable of 60 amps and pulsed up to 309. Now that's not the full story. Let's look. Here's all the applications. Class D audio, of course. So high frequency switching, high efficiency, small footprint. The other thing is very low thermal resistance. This guy is thermally connected to the board. So that's another big advantage that's I don't think is passed on as much as it could be. This thing's going to get hot because it's so small, but yet it's going to be very, very little thermal resistance to the board. And look at all the data that you can get with this. Okay. Lots of stuff. All right, guys, so let's look at the schematic. Now, I'm going to do a rant about schematics, and these guys give me a lot to rant about. So let me know if you want to hear what I have to say about schematics, because this schematic is terrible. The VN's on the left, V out's on the right. This is the support components to support the 16th brick right here in the middle. Okay. And here's test pins over here on the left bottom, right bottom, V out, test pins. And yeah, so that's the board, the support board that this thing plugs into. Let's look at the schematic for the brick. this guy right here. It's called B1, brick 1. All right, there it is. There's kind of an eye chart zoomed out. You can see the control chip here in the middle and a bunch of capacitors all over the place. Output FETs. So here's 4 GaN FETs. Here's the output inductors. And here's a control chip. Let's just zoom in and look at the control chip. Did I say I was going to rant about schematics? Yes, because this schematic is terrible. It's like they follow all the things not to do on how to design a schematic. They know how to make GaN FETs, but not so much schematics. So here's 2 GaN FETs. Here's an inductor, and there's V out, okay? And repeat up here on top. And these guys, the V out, they parallel together right there. Okay, so we have this chip right here running the show. Okay, let me show you over here on the left side of the schematic. So VN, so this is VN. We got 1, 2, 3, 4, 5, 6. So we got 12 220 nanofarad capacitors, or 0.22 microfarad, otherwise known. We also have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1 microfarad capacitors, okay? Yeah, so we got a lot of input. Wait, I see more stuff. VN. Check it out. Another 1, 2, 3, 4, 5. They like that value, that 220 nanofarad, 0.22 microfarad. They got another 12 of them here. So lots of input capacitors. Okay, let's scroll over here. And now we're looking at output. Oh, this is still VN. So look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So another 10 capacitors for VN. So altogether we have 20 of these, and we have 24 of the two. I mean, that is a lot of ceramic capacitors. Where's the output capacitors? Okay, here we go. Down here in the bottom left, here's output. 1, 2, 3, 4, 5. Did I say I wanted to rant about schematics? Yeah. Here's another 10, 22 microfarads, 25 volts. So they're derated nicely because we're 12 volts out. So that's more than double the voltage. That's awesome. Input, 100 volt caps. That's great. So that's good. Yep. Good electronics design, just poor schematic. It's too bad. Oh, look, we got more output capacitors over here on this side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Another 22 mics. So, okay, we have our 2 outputs right here, but we have our output capacitors over here on the bottom left, or here on the bottom right. Our inputs are scattered all the way across the top and across from input to output. So, interesting. I am going to rant about schematics this weekend, I think. Okay, guys, here's the little module. Okay, there's my connections. So I've got 1 scope probe on the input power and 1 scope probe on the output power on these test points. Okay, we're going to just do a simple check, just see what the ripple looks like. Now, okay, and there's the power supply. See the yellow and green wire? And I've got it set for 27 volts. It's hard to see with all the reflections. And it's 2.3 amps max current set for. So max watts right now is 62 watts. We're going to just see a lower power, what it can put out. Because I have to put a fan on it and some other stuff to get higher power. Okay, so then the active load is right there. The IT Tech. And it's set for 3 amps. So when I turn that on, we'll get 3 amps out. And then the scope we're going to use is the Uni-T. It's the MSO 3054 HD. HD, high def, so 12-bit. Right here, 2.5 gigasamples per second, 12-bit. 500 megahertz bandwidth. So there we go. So I captured the ripple on the output. That's the yellow one. And on the input is this purple one. So we're at 50 millivolts per division, and it's about 50 millivolts. And you can see this kind of cyclic hump. Now we're at 1 microsecond per division, and it's like each division starts a cycle. So it's about 1 megahertz ripple there. Now the output ripple is interesting because it's a little bit lower frequency, but it kind of seems like it lines up with the input ripple, right? So it seems like this one here has this little spike here. You can see these spikes as switching voltage, but we have this little kind of lower frequency, about 500 kilohertz ripple. But that is impressive because it's 10 millivolts per division. So 10 millivolts peak to peak. That's pretty darn good. And it looks pretty clean too, right? So I think we're liking this. All right, guys. So what we captured here is the yellow is the input, okay? And that's the ripple voltage on top of it. So it's AC coupled. So it is 500 millivolts per division. So some of this spiky stuff, it's just because of the probing technique. I could get it to drop that by using better probing technique. But there is, you can see when the bottom waveform is a switching node that we just probed. The voltage is down here is 0 when the lower FET's on, and then the lower FET turns off, and then it goes up to, let me touch that scale. So then it goes up to 30 volts. So when I touch the scale, which I'm on, it changes the scale here. So, so it's 0 up to 30, okay? And this is 10 volts per division, so 10, 20, 30. Now the output's about 12. So it's not quite 30. Let's say it's 28 or something. But then the pulse width, it's not on as long as it is off. So if you took the average of that, you know, you're going to get the 12 volts output, okay? So the inductor smooths it all out, makes it 12 volts. So when the bottom FET turns off, it's on down here. When it turns off, it comes up, there's a spike because it came up so fast, and it transfers the spike to the output, and then it comes across, and then it turns on, and it stops here, and there's a spike there, and a little bit less of a spike burst there. So you can see that going over and over. That's when you look at the output. You can look at the frequency by looking at two tall spikes, not looking at the two spikes next to each other, because you know one's on, one's off, one's on, one's off, kind of thing. So when you're looking at ripple on the output, usually you'll look to see if you pattern like big spikes and little spikes, so you can tell what the frequency is. But yeah, that's a nice clean picture. Yeah, the scope is an awesome scope. So there you go, guys. Pretty cool, huh? It looks fairly clean. Okay, there's not a lot of ringing or anything like that. And if I spread this out, so you can see how the waveform comes up, overshoots a little bit, comes down, dampens right out. So it actually looks pretty good on that side. That's the turn on side. And then if I scroll over, we can see that's where it turns off. Let's come over here. I can do this. I can scroll over faster. Okay, and then spread it out again. So you can see when it turns off, it comes down, comes up, and dampens right out. So it actually isn't too bad at all. And this is easy to filter on the output. Some of this stuff is just high frequency stuff that's picked up on the probes, amplified by the loops, you know, the antenna type structure in the probe, because I'm not probing with a little spring clip, or, you know, I'm adding a little inductance to my reading, so it's amplified. But I can also filter, LC filter on the output and clean that up even more. So there you go. So what do you think of this little board? Pretty cool, huh? I didn't show you the back side. We saw a really good picture of it, so I didn't take it off the module, but I could carefully, you know, pull this off this carrier card, this evaluation card, and we just have the little module. But Yeah, that's pretty neat. If you guys want to see me do some more probing on this, like look at some more waveforms and uh, put more power through it, I got I got a couple fans here. I can just blow some air on it. When you start getting hot, I mean, it's just sitting there in the air. There's no heat sinking off the board. So that's a very small board to dissipate power. But if it's tight, and it does have the big pins going down to this card, which has some copper on it. But when I took the thermal pictures, you can see it's not transferring any heat. It wasn't really set up that way. It would have been kind of nice, but maybe they want you to evaluate how this thing runs on its own without heat sinking. So, yeah, there you go. That's pretty much requires a fan, okay? Or if we put it on a heat sink, but it's hard to probe it and look at it with the heat sink on it. But there you go. That's pretty cool. That's EPC's evaluation card. EPC9534 is what this board is. But you can take those files and, you know what? Let me know if you want me to go through the Gerber files, the design of that. I do kind of want to rant on their schematics because, man, I'll tell you what, they took all the bad things that are happening in schematics today and combined it all in one drawing. I mean, they did. I don't know what you guys thought about those drawings, but they're terrible. So I think I might do a rant tonight. I might have a beer and rant. Let me know what you think of that. So, all right, guys, thanks for watching. Appreciate it. Hey, thanks, EPC. Big thumbs up. All I have to do is ask them. They send out these modules for me. That's so nice of them. Their design looks amazing, awesome. It's just their schematics are terrible. I think a lot of that has to do with, well, I'll save that for a rant. Okay. All right, guys. Thanks for watching. We'll see you next time.